Good morning, ladies and gentlemen. This is the second day of our online training on HOMER software. Yesterday, we had covered the introduction part of the HOMER software, its simulation optimization aspects, the simulating and the payback period, internal rate of return, some of the basic functions of the software. So now we move on to our today's session, in which we will cover the topics such as refining design, developing a customized load, sizing diesel generator, size technologies using specific sizes, and exporting data. So these contents shall be covered by Dr. Peter and Mr. Silverio. Ladies and gentlemen, just for the knowledge of the participant, the contents of this online training are available on our website. We have shared the link on the chat box. So all the data and materials are available. So for today's training session, the specific material is already uploaded on the website. On the website, you can download it, which will be required during the course of this today's training. So over to Peter and Silverio. Over to you, sir.
Well, thank you, Hassan. And thank you all for coming back today. I hope you enjoyed yesterday. The goal yesterday was to do a quick design. Let's say you're early in the process and you just want a conceptual design, and how can you get results quickly? The goal today is going to be to refine that into using more detailed data, both load data and also instead of using our optimizer, use our search space, two different optimization algorithms, as if you had specific sizes, to choose from instead of just letting HOMER pick any size at all. After the first phase of conceptual design, you'll have you'll know, oh, we need, let's say, 23 kilowatts of PV. Well, they come in either 20 or 24. So that's the kind of thing that you handle in this refined design that we're going to be talking about today. And just like yesterday, Silver will do most of the talking, and I'll provide a little input as well. But I'm going to hand it back over to Silver now. Over to you.
Okay, thank you, Peter. So today, as discussed, we'll be going more on the details of building our HOMER software. So I'll just show my screen. Okay. Can you see my screen now?
Yes.
Okay. So we'll start with this.
But your microphone is not great. I hate to say you have to hold it in front of your mouth the whole time. See, it worked better yesterday. I don't know.
Oh, sorry. I'm not sure. Maybe the connection is kind of loose today. Can you hear me still?
Yeah, it's just not very good.
Oh, right. Can you hear me better, or?
Oh yeah, that's much better.
Yeah, that's better.
Okay, I'm using the computer microphone.
Yeah.
Anyway, so can we proceed now?
Yeah.
All right. Okay. So today we'll be discussing more on the details of modeling our load, and also having specific sizes for our genset for a sample system. So it was discussed yesterday that loads are crucial in terms of designing the power system around it. So using the HOMER software, we can actually model the load, and conveniently, without any information on the details of the load, HOMER can provide a type of load that you can use. So on the load setup window, you can select a pre-designed residential, commercial, industrial, or community load. You can also leave it blank if you have you want to input on the specific details of that load. So for our sample load, we can, let's say, start with a blank load and click OK. And with this blank load, you can see the hourly time there on the first column and the load in kilowatts on the second column. So we can fill this manually. So uh, what I
You want me
prepared
to
is a
read the
yes.
numbers to you while you put them enter them, Silver?
Uh, I
Or
can
oh yeah, you can just do that. Sure.
okay. I can click on an Excel sheet and go back to my HOMER file, and I can paste that data on the uh, input side of the load. So you can see the hourly data on the kilowatts of the load, and the peak loads are happening in the evening. So this one way of putting in data on your HOMER file. Okay. So just to go through the information here, uh, you can look into the, because we have just made a sample day, and HOMER spreads it throughout the year as if just the regular profile you're doing on a daily basis. So you can see on the D map below, it's constant throughout the year as if it's a
Every day,
program load. Yeah,
every day is the
every
same.
day is the same. Very boring type of load, but probably it is a time, like a sample time load. Now, to be realistic about it, uh, every day doesn't have the same load. So you have here random variability. So it's day to day and also time steps. So if we go to a sample data uh, using the HOMER files, so we can remove this
Well, hold on.
first.
Before you do,
Yeah.
Silver,
Okay.
because we get questions a lot about that random variability. So if you don't mind, I'll jump in and explain it a little bit, because
Okay. Sure.
obviously every day being the same isn't realistic. So how do we make it more realistic? By adding variability, and we do that in two different ways. There's two parameters there. Um, so the value that you put in there is the standard deviation of a normal distribution. It's a little math. Um, but basically, if you put 10%, let's say, in the day-to-day variability, and then click
Okay.
outside the box, you have to click outside. So you can see it added some variability there. It maintained the same shape. Every day still has that shape that you see in the upper graph, but some days are just bigger, have a higher load than others. Like, relatives have come to visit, or everybody's out, gone somewhere else for the day, or what it's a holiday, or there's just going to be times when the whole day is a high lit day or a low day. But then the time step variation varies randomly for each time step, in this case, each hour. So if you put a 10 in there and then click outside the box, you can see it added more variability. And as it did that, the peak load was increasing as well, because now you've got some high days and low days. But if you also notice at the bottom, the scaled annual average there at the bottom is 0, because that was what it was originally. So Homer's going to scale all this data based on that number. So we wouldn't want to leave it at 0. You'd want to make the annual average equal whatever the actual annual average is. Right. So the data we put in over on the left came to 184 kilowatt hours a day, but we're scaling it. So same shape, we're just scaling all the numbers down to 23.3. Or
Oh,
you,
yeah,
or
sorry.
yeah,
Yeah,
so
so
right. And so
grid and
now it's
equal
the same.
scaling. Yeah.
Right. So I hope that's clear. And then what, Silver, you were going to show how to import data. Is that what the next thing was?
Yeah. Oh, thank you, Peter. So in this case, we introduced uh, an input data on the table, and then we also introduced the day-to-day variability and also the time step data. So
Actually,
Homer
Silver, I'm sorry.
provides,
Sorry to interrupt again. One more thing we ought
yeah.
to show is that button that says show all months. If you click
Oh,
on that,
okay.
now you can put in seasonal variability. It's got, initially it didn't have it made every month the same, but you can come in here. It's a bit more work, and change and so you can def define the load varying across the year explicitly with this table here, and whatever, and then it's you can make weekends and weekdays different if you want, but the checkbox at the bottom is checked, so it's in this with that check, the weekends are going to be the same as weekdays. Um, and the copy changes are right. It's just a convenience. So if you just want to do 4 seasons, you can um, put in January, it copies to right. Put in April, then it copies that to the right. Put in to July, and it copies that to the right. So then you only have to fill in 4 columns if you want to do it by season. But so I thought I'd show that as long as we're doing the more detailed design work. So, sorry to interrupt, Silver, but I
Yeah,
thought
thank you,
show
Peter.
that.
So also to emphasize weekend and weekday load, because that also is quite significant in like offices and schools that have a different load profile than the regular weekday. We can click on, uh, we can change the weekdays and weekends. Let's say we can reduce the load during the weekday, during the weekend, sorry, to instead of having a peak load at night, they may maintain that 11 kilowatts uh, until midnight. So if we click OK, you can see that there is a very distinct gap, change in the weekend loads. So that's one way of also having a distinct load profile during weekends and holidays uh, uh, for loads like schools and offices. Okay, so that is the way of modeling load if we have those data or we have this sample data. Now, another way of utilizing the load is to import uh, a load. So we can first, if before changing a load, we can save this. So we can also export this load, and we can name it, let's say, sample load, and it has a DMD uh, file type. That means a demand file. So we can save that, and we can import. First, we remove this, and we can import a load, and we can have, let's say, uh, this sample file included in the folder, and we can open it. And here it shows the year of when was that load taken, or what that specific load is still true, because if we apply load growth, then Homer can project that. Let's say that it was taken in 2011, so Homer can mark that up, and you can see this file. So we have already imported the day-to-day variations and also time step variation based on that load profile. So that file is actually composed of 8,760 hourly data for a 1 year worth of load information. So here you can see the daily hourly variation throughout the day and also the
Oh, he froze. So
seasonal
Silver, you froze.
variation throughout the year. Okay, so that's one way of using. You can see that the peaks are already recalculated. So as mentioned by Peter earlier, we can rescale the value of uh, the energy, the daily energy of this load profile. Let's say additional load had increased or more appliances had been added. What Homer will do is just scale up the energy, and let's say from 184, we can increase it to 200, and then we have a scaled uh, profile with a daily average of 200 kilowatt hours per day. And as you can see, the peak load also increased a bit because we have increased the energy. So we can change that according to the model that we are working on. So we can go back and bring it back to the original form. Okay. So the variability of the load also affects the peak. So it also changes the type of the capacity of the gensets or power system that we will be modeling. Okay, so let's
Uh,
say we will.
Silverio, can I just make a comment? We have a question
Yes.
from Ali Qureshi. He's saying that could you explain more on the scaled annual average? What's this?
Okay. Peter, you want to answer that or?
Sure,
Uh,
sure.
okay.
So like when silver increased, well, go ahead and do that now. Put in a much bigger number. Say make it 300 or something. What
Okay.
it's doing is it's scaling all 8,760 values by the same amount. So it's preserving the shape. It's preserving the daily shape and the seasonal shape, but it's just making everything bigger by the same amount. But it's a multiplier actually. Um, it's very important to get that right, obviously. A lot of times you don't know really what the shape is. You have to estimate the shape, but you do know what the average, the average consumption is. You have like a total, you have the total kilowatt hours. Um, so so we this way you can estimate the shape and then scale it um, to whatever size you want. And you can see the little round button next to it, just like on yesterday with the fuel price and the capacity shortage. You can do a sensitivity on that, so you can see, well, here's what the least cost design would be if the load was 184 kilowatt hours a day. But if we did a sensitivity, it'll give you results for whatever values you put in that little sensitivity value editor. So I hope that was an adequate response.
I yes. I think would in my mind it would be something like if you could increase the load up to 10% or 15% and do the sensitivity analysis on these three parameters.
Yeah,
Then, if that's the case.
yeah, exactly. So you can you, if you want to do 10%, let's say your baseline was 300, you do 300, 330,
Mhm.
360, and that'd be 10%, 20, and 20%. Um,
Okay.
and so that you could, right.
Yes.
Yeah, you
And
can.
of course, it'll take
You
3
can do
times as
this.
long too, also. But go ahead. Sorry.
Yeah. Okay. Yeah, you can do sensitivities like this. But I think Peter, you wanted to mention the multi-year option for Homer.
Well, that I'm not sure I wanted to get into that this early in the training. But I'll mention it that and it's a relatively new feature. So if you close this, actually, I'd remove those sensitivities just so that it doesn't take so long to. Oh, I don't know what we're gonna do when we calculate. I want to calculate based on what's in the manual, but after you put that back at 184, I guess, and you go up to project, I'll just show you how you get into the multi-year. So it's up there, see where it says multi-year, and now you can put in you have to enable it with the checkbox, and you put in the lifetime, and now instead of modeling 1 year, it'll model 25 years, and of course it's going to take 25 times as long as well. So you have to be careful not to get carried away trying to do too many things at once, or
Yes.
and depending on the configuration you've laid out, you'll have a number of variables that can escalate. So right now, all we have is a load. So we just have the 2 things that we can escalate: the scaled annual average, if that's assuming load growth, and we haven't talked about these system fixed costs. But that would be like administrative costs, and it doesn't
Fuel
affect the
cost can
optimization.
also increase. Yeah.
Yeah, and we can do it in 2 different ways. We can put in where it says 0 there now. We can put in a number and say like 5. If we put a 5, it's gonna increase 5% per year every year. But if we click on that button that says years, we get a table. Click on one of them just to show. So now it's showing what 5% a year would look like, but we can go in and change those numbers. So a lot of times people have an idea of load growth where they say, well, we're going to put in this system, and it's going to take a few years before people start buying appliances. And so there's not going to be a lot of load growth for the first couple of years, and then there's going to be a lot of load growth for several years, and then it's going to taper off again. And so it's not going to be a constant 5% a year. So you can actually put whatever kind of trajectory you want by filling out that table there. And so maybe we'll revisit this when we have more components in the system. You'll see there's more things that you can escalate, more different kinds of costs that you can escalate.
Okay. There's
You
also
can't.
a hockey stick kind of increase. So as Peter mentioned, there's
Sometimes,
a
yeah.
time
But
that people adapt. Suddenly, the load increases and then it tapers out. Yeah. Okay.
but before you close it, unclick enable just so it doesn't run.
Yeah. Okay.
Runs fast. Yeah.
Silverio, we have a question from Asad Iftikhar. If my load data is from June 2019 to July 2020, while importing, what year would I define? And also, if I want to import minute level data, is there a way to do that in .csv or XLS format? I can currently do only in a .txt format. However, it does not allow me to add timestamps.
Well, okay, so there's 2 different questions there, and I'll answer the first one first. You can import you can import minute level data. Of course, that's a 500,000 pieces of information. But it'll recognize, oh, I've got 525,600 data points. Therefore, it must be minute data, or if it's 10-minute data, it figures that out. And I don't know if you noticed, there was a choice: import and edit. So a lot of times there'll be holes in the data, and the edit function allows you to fix that. So it'll import any resolution, but it has to be a full year. And but with the edit function, you probably can fix that. You set a TXT. So what we do is, if you take that TXT file and put it in Excel, then you can export the Excel as a CSV file. Actually, there's several different formats that we can accept data in. It's under help. You can see the different formats. So so we've expanded the number of the different formats. So without going into the help, I'm not sure I could explain all the different ones. But the help explains it. Because sometimes it's initially, if you go back 10 years, Homer would only accept a single column, just the numbers, and now we can do it in 2 columns. We can do it in multiple different formats, where the first column is the actual date and time, and then I don't know. This load data comes in many different formats, so we've tried to
Silver?
make it capable of handling any format.
I think Nidhi has
Yes,
to comment.
yes, Nidhi.
Silver,
Yeah,
I might want to add a little information.
sure. Go ahead.
Silver, can you go to the load, electric load 2? Can you add that? Maybe electric load 2. And then we have this
Okay.
little I over import a load from a time series file. Little I over there. We have a link. Yeah. So this link directs to the format which can
Oh,
be
good.
taken.
Thanks. So maximize that in the upper right there, yeah. Although so Needy, which of those is the? Oh, there we go. So here's the different formats. That's
Yes.
and just scroll down. So there's a 3-column format, and
There are 6 different options in which the load can be format. Just the one restraint is it has to be a multiple of 365, and then it has to be .csv data file.
right. Yeah, so we probably
So
won't go through this entire help right now. Needy, do you want to say
Yeah.
something else? Actually, Needy, it's not a multiple of 365. It's multiple of 8760, wouldn't it be?
Yeah.
yeah, sorry,
It's
sorry.
composed of
Yep.
hourly data for
Hourly data.
365
Yep,
days.
sorry about that.
So
Yeah.
yeah, so that's on an hourly data. So you can see here, that's the year. So this is more explanations on importing load files. And Peter, that would lead to the next question on importing minute data.
Right. So you probably couldn't, some of these formats probably won't work with minute data, like this one we're looking at right now. I don't know, Needy, do you know whether that would work with minute data? Some formats will definitely work.
First 2 should work with all type of data formats.
And this last one as well. This was the original one, this option 6. That was the original. So let me answer the other question that he asked, which is so the only reason we ask for what year is to get the weekends and weekdays right. So Homer assumes that the first, well, make sure I say this right. The first data point is going to be midnight to 1 a.m. on January 1st. But what day of the week is that, right? So so it actually doesn't really matter if Saturday was on January 7th or January 5th. It's not going to affect the results, but sometimes people, like to see it look right. What we do when you have data like you were describing from July 1st, 2018, let's say, to June 30th, 2019, is we'll splice them. So we'll have, let me make sure I say this right. So we'll have January 1st to June 30th of 2019, and then we'll splice in July 1st of the previous year to the end. So it's not going to be perfect in that situation because you might not get the weekends and weekdays might be off. It's not really going to affect the results, though. I mean, it's too small an error to affect the results. But that's what we do is we splice the two halves to make a whole year, one consecutive year. I hope that was clear.
I think an important point is that you can't just import that data which has half previous year and half this next year and just call it a single year, because otherwise the whole seasons would be what do you call it, mixed together.
Oh, right, exactly. Homer's going to assume the first line is January 1st.
Exactly.
So that's a good point, Hassan, to clarify that.
There can be a workaround. You can copy the January to June data on top of the July so that it becomes a year data.
Well, that's what I was trying to explain.
Yes.
Hopefully I explained that well enough.
You're good, Peter.
Okay, please go ahead.
Yeah. So what's next? Manually sizing the generator?
Yeah. So we
Oh, you want
can,
to show this?
yeah, just what Nidhi was mentioning about having these changes to the right. So if you have limited data, you can copy that to the next month. So the more accurate the data, the more accurate the Homer can model the system. Okay.
Yeah.
So yeah. So in some cases, I would install a data logger on a site to have hourly readings, but sometimes as close as 15-minute readings, and make hourly averages and put it in Homer so that I have more accurate data to work on, right? So next would be adding a power supply system. So we have a red warning here requiring us to add a power source. So for this case, we'll just use a genset. So yesterday, we were using auto-size genset. Now, if you go to the store or look into a catalog, they have specific sizes of the genset. So we can look into, let's say, a 50 kilowatt genset that's off the shelf and add this to our system. So for now, we'll just use the default data, and that's specific for a 50 kilowatt genset in this example. So you have here on the schematic a complete genset and load system. So if we click on calculate, Homer will simulate the system and show you on the first screen the summary on the configuration. So the system architecture is composed of a 50 kilowatt genset and powering a load. So you have here replacement cost for the genset, fuel cost for the genset, salvage value at the end of the 25th year with the remaining value of the genset, operating cost, and on the first column is the capital cost of purchasing that genset. So you can see here on our table as shown yesterday, net present cost is 963,163. So our cost of operating the system in terms of cost of energy is $1.1 per kilowatt hour. And it also provides us information on the fuel. What would be interesting is on the electrical part will be some excess electricity. We'll emphasize that later when we,
Well, a lot of
uh,
excess electricity in this case.
yeah, there's a lot, like 41% of excess electricity. This is not often seen when doing rural electrification, that supplier provides a genset out of the warehouse and assume that it will work to power the load, but they don't consider the, the excess electricity that would
Yeah.
be
And
spent
that's
in operating the system.
so we use the 50 kilowatt generator is just massively oversized, which is we find is common problem. People put in an oversized generator, and so it's the minimum load constraint is what's creating all that excess electricity, because there's times when the load is below the minimum load on the diesel. So Homer is basically assuming there's a dump load. Um, um, so the next lesson is going to be sizing a second smaller generator, and just to see how much more efficient that is.
Okay.
Right?
We'll do the comparison later. So I'll just show you something on the time series. And if we look into the excess electricity, we can go down, and here on, okay, the second column will show that parameter on the lower part. So there's a regular excess generation because of the capacity we selected for the genset is 50 kilowatt, and the demand is only around 20 kilowatts. So there's a lot of excess.
Yeah,
Now,
every time that black line on the upper graph is below the orange line, the load is below the minimum load on the diesel, and that's what's creating the
Yeah.
excess. Right.
Yeah. So what Peter mentioned is every time that black line goes below that orange line, that means this is the minimum demand required by our 50 kilowatt genset, then there are losses. So often in practice, they would put a dump load, a dummy load, a saline solution to absorb that excess to maintain the loading of the genset. Okay. Right. So
Value, can I
yeah.
just most of the time we have seen that we are designing systems based on the current requirement and current load of a community. But we have often seen that once the load is connected, the power is available to them, then their load requirement increases drastically in next few months. So could we make some provision of putting some extra power sources just to cater for the increased demand, which will most probably increase in next few times after the installation of the system?
Oh, well, we're going to have
Yeah.
a lesson where we have a small generator and a large generator, and that
Okay.
I don't know. Was that the very next thing, Silver? Or is there something else?
Yes, exactly. Like for example, if you are putting up a diesel generator of 25 kilowatt based on today's requirement, maybe the community might require increased amount of power in future. May it be diesel generator or the solar PV panels, but the overall requirement may increase. So does Homer incorporates this kind of forecasted increase in requirement or not?
Well, if you use the multi-year, you can put in your estimates of that load growth, and then it will make sure that it puts in a system that can handle the load growth. The problem is, though, if you think, well, in several years the load will be 50 kilowatts, well, you want the generator to be a little bigger than load. Let's say that you think the load's going to be 40 kilowatts, so you put in a 50 kilowatt generator because that's what you think the future load's going to be. Well, in the first couple of years, that generator is going to run really inefficiently, and it's actually bad for the generators to run at low loads.
Right.
So that's why often it makes sense to have a small generator and a large generator, unless you have a lot of renewables and batteries. And nowadays those generators are mostly just backup anyway. Um,
Okay.
um, So back
So
to
we
you,
can use,
Skipper.
so we can use that option of multi-yearly in which we can
Right.
increase the load balance.
Right, right.
Yeah. First, we try to add a smaller genset just to see what would be the effect. So let's say click here, smaller gens, and then we can do a 50 kilowatt at, let's say, a 25 kilowatt genset. Okay, so
Well, we should point out, I'm sorry to keep interrupting, Silver, but I do want to point out that there's two different kinds of generator screens here. The first one says fixed capacity, so it's 50 kilowatts. The second one says size your own, and so over on the right you can see there's a sizing um, table. So
yes,
there's these two, depending on what kind of generator you have, they're slightly different. If you've got the fixed capacity is meant to be, well, we have a catalog, say Caterpillar or Kohler or whoever, they make generators in very specific sizes. Those are your choices. And so that's in the catalog. But if you're just trying to figure out, well, approximately what size do I need, you can use these size your own. The inputs are a little different, as you can see.
okay. So we can use this assumption and have a size of 25 kilowatt. So as Peter mentioned, if you have a catalog of a 25 kilowatt genset, you can also use it here. Okay, so we maintain the same fuel cost for both genset, and we can simulate which one would Homer prefer, or and if a combination is also possible. So we'll click the calculate button, and Homer will provide three different options for the system architecture. So our previous system or baseline data is having that 50 kilowatt genset, which now is on the bottom selection because of the highest cost of energy and highest net present cost. And then Homer ranked the smaller genset at 25 kilowatts to have the lowest net present cost and cost of energy. But this is based on the load that we have forecasted for that particular year of 23 kilowatt peak. Now, it also Homer also provided an option to combine the two gensets, and as you can see, we'll look into the specific system and go to the time series. We can see that you have two gensets, but the default color that Homer would use is the same. So we can change also the color for the auto-size genset, maybe this dark red. And just to zoom in, and probably better to have next column.
Well, in this case, the larger generator is never getting used at all. So if you made the smaller generator smaller than the peak load, then the large generator would get used a little bit.
Okay. Come again, Peter?
Yeah. Well, so close this down and just make the small generator like 15 kilowatts or something, so that it runs
Okay.
when the loads are low, and then you still need the large one. So close this down. Go back to the.
All right. And we go back to our system.
Yeah,
so this is the 50, but we need to change this. We just have to label this new genset or additional genset.
Yeah, additional small generator.
Or small. Oops, sorry.
And then
And
fix the abbreviation too, because that'll get confusing. I'd say make it 15 kilowatts. 15. Oh, yeah.
we'll change this to 15.
Yeah. Right. And so this will be more interesting results. So hit calculate.
Yeah, so we have the basic 50 kilowatt and then a small genset. Maybe we
Right.
can put here Gen 15 just to be clear about it. And we can do the calculation. So it doesn't have a 15 genset only system because it's too small to run the load.
But you can see that the cost of energy now is less because the 15 kilowatt generator is just less costly to run when you can, and it runs most of the time, 7,565 hours over on the right there, and the large generator only runs for 11 or 1,200 hours a year.
Yeah, so here
that's more efficient.
the 15 kilowatt genset runs most of the time, and we can go down the detail of how they work by looking into the time series. Again, we can change the color. And probably, yeah.
And blow it up, maximize it, Silver. It's easier to look at if you maximize the whole window.
Okay.
Well, it's not that important.
Yeah. So the load is the dark line, and let's say go down, and the 50 kilowatt generator is that orange line, and the red line is the smaller 15 kilowatt genset. So as you can see, if the load is small, it's only the small genset is operated. Then when the load increases, the 50 kilowatt genset kicks in and turns off the smaller genset because it can efficiently operate at this load level, and it's too high for the smaller genset to operate. There's no need to combine both because then the load will be too small for both of them. So this is how HOMER would simulate the best, let's say, this past strategy in how the two gensets would operate based on the load. You want to add something, Peter?
No, I think that's good. I like to maximize the window, but that's not important really.
Yeah. Okay. Sure. So yeah, we have this load on the dark line, and then the small genset on the red line, so it's operating most of the time. But during peak loads at night, the big genset kicks in. So in this type of system, you have two gensets working one at a time, depending on how much load is needed at that specific hour. So we have questions from the audience at this point.
Yes, Silverio, we have a question from Saad Mansoor Rana. Can HOMER takes into account the efficiency / heat rates of a genset because the consumption of fuel is affected if we run a generator at different loading positions?
Oh, absolutely. Yeah. So you should show the fuel curve inputs.
Okay, that's a very good question and important point. So let's say we go to the 50 kilowatt genset, we click on advanced, and we can see the fuel curve, both on the first curve is a linear curve showing how much fuel is consumed per hour, depending on the load.
Liters
So
per hour.
Yeah, liters per hour. Depending on the kilowatt of load. Now that's the fuel consumption curve. It's almost a straight line. And you have efficiency. So this is the efficiency of this particular genset that, as you can see, it starts at this point where it has a minimum load, and you have this efficiency curve. Notice that the efficiency is less if the demand is if the load is smaller.
Yeah, so
So it operates better at higher load. This is how
that's
Homer would then select which genset to operate based on the load and the operating uh, demand of that particular genset or set of gensets.
yeah, so that's what the questionnaire was referring to is, and so Homer, absolutely, it's super important to capture the part load efficiency of the reduced part load efficiency. And you can input that in two ways. The when in the linear curve, when it's liters per hour per kilowatts, it's a linear curve, and you just need an intercept slope and an intercept. But an easier way to do it is this fuel curve table, because usually the generator manufacturers will give you, here's the liters per hour at 100% load, here's the liters per hour at 50% load. You really only need 2 points, but they usually give you 4 points, 75%, 50%, whatever. So if you fill out that table there, it will use that data as the fuel curve. And you can usually get that data from generator manufacturers. Of course, it degrades over time, but
Yeah, so you can actually change that this data with the manufacturer's catalog to have that curve.
So,
yeah,
question from my side, Silverio, just a comment on we are designing these two generator systems for our load. So, if I mean, what I'm seeing is that you are putting 50 kilowatt of a single generator, big generator, and then you are trying with a 25 kilowatt small generator. Then you move on to 15 kilowatt small gen, and you are checking the calculations and the results. Obviously we would like to reduce our cost as much as we can. So can this HOMER software based on our load recommend us a big and a small generator with such a configuration which could reduce our cost as much as possible? You got my point.
yeah. So the size your own, that when if you go to the small genset tab, so if you over here on the right, if you give Homer lots of choices, it will find the least cost option. So
That's
that's
good.
the value of the size your own. Either based on whatever generator options you have, actually.
You can also have compared to the 50 kilowatt genset, which is huge. The catalog may also offer you 5 kilowatts, 20 kilowatts, or 25 kilowatts, and you can see which one would perform best out of the choices for a smaller genset. So this is the purpose of the sizing table, that you can use the same small size genset using the same cost per capacity and scale that to different sizes of genset. So we'll just try to run this. So Homer will try to simulate the 50 kilowatt with the different sizes of genset. Now we provided Homer with 15, 20, and 25. Now you can see the best to combine with the existing 50 would be a 15 kilowatt genset. Okay, but if you want to size a smaller genset and a standalone one, Homer selected the 25 kilowatt genset, so it can operate on its own with a small system. And of course, our baseline 50 kilowatt will be there. So this is
Actually,
under the categorized system. But there are several combinations of those 15 to 25 kilowatt small genset that can still operate. Yes,
this is a good
Peter?
time to point out something that's important to point out. We gave it a choice of 15, 20, and 25 for the small generator. and it said 15 was the lowest cost. And that leaves open the question, well, if it picked the smallest choice we gave it, what if we'd given it a smaller choice? So and I bet if you go to design page, design, well, no, all right, never mind. But go back to the 15 and put in 5 and 10 just to see what happens.
Okay.
No, don't delete anything. No, don't delete it. Leave the 15.
Yeah, all right. We'll just add here 5
Yeah, 5
and
and 10,
10. Okay.
and recalculate. Just because it picked the smallest one, we gave it the option of picking, and it turns out that actually is the best thing. But we didn't know that until for sure, until we made the runs.
So that comes to another question. Could we change the limits of the bigger generator too, like 50 to
Yes.
60 or?
Well, we'd have to make it a size your own, but we could easily do that.
Yeah, so what we did was to select fixed capacity genset for the big one, and the size your own for the smaller one. But if you also want to have select size your own on the larger genset, you can also do that. So let's try. We can, let's say, remove this because we can easily add that later. And here we have choices of adding a genset. So there are fixed genset capacities. You also
So
have
go to the he doesn't want a fixed capacity. Go to the medium size.
yeah. Okay, so
that one. Medium,
we can go here,
yeah,
size your own,
yeah.
and add that genset. Now we can have 0, that means only the small ones will be used. Then we can say, let's say 40, 50, 60.
Well,
That's
it's
relatively
not
larger.
gonna. No, do 30. It's not gonna want a 50 or
Okay,
60.
all right.
But
30 then,
30, 40, 50 or something.
40, 50.
Yeah.
Okay.
Yeah.
So this is and let's say this is the engine size, genset.
So,
So
so right.
just
We should have changed the name instead of calling it 15, and we just call it medium. Yeah. Yeah, that's good.
all right.
So hit calculate.
So what it does is Homer will try to calculate uh, the combination of
Oh,
the
so
large
that's
and the
really
medium and the
interesting.
small.
So now if you have if the larger generator is smaller, then the small generator can be smaller as well. And now we've gotten the cost of energy down even more.
Okay, I'll first go to the categorized list so that
Yeah, a little easier to look at.
see that. Okay, so the smaller genset, it selected a smaller one, and for the medium genset, it selected the smallest of the choices we provided.
Yeah.
And you see, we don't. If we go back to the overall and look for that 50 genset, we can see that the cost is, yeah, here is 0.931, while our cheapest system is almost half of that. Okay,
And
so
really, I don't know if we should move on or not, but because 30 was the smallest size we gave for the large generator, maybe, I'd normally want to check whether that should be even smaller. But maybe I don't know if we should move on or not.
Is it possible
yeah, so
that
But yeah, put 25 and 20 in there, and And the default values, just so you know, for on our medium generator is a more efficient generator than the small generator, so that it has a better fuel curve just because in general larger
Yeah,
generators.
yeah.
So
The fuel
hit
curve
calculate.
of a small genset is not the same with the medium and the larger one. So it further went down to 20 kilowatts. Okay,
Oh,
for that
and
medium genset,
and
and it selected a.
it's assuming that we can parallel those two because
Hmm.
occasionally, not very often, the peak load is greater than 20 kilowatts. So it Homer is assuming that there's the ability to parallel those two, which probably
Yeah.
isn't there, But so you'd want the large generator to be big enough to meet the peak load, I think.
But
Yeah. So
this
if you
configuration
go
of
back to the result.
yes,
Go ahead, Hassan.
yes. My question is that this configuration which Homer has recommended us of a 5 kilowatt and a 20 kilowatt generators, it surely is going to cover the peak loads, right?
Yeah, absolutely. Unless we allow, remember yesterday we allowed some capacity shortage. And so then it might not, but if we set the capacity shortage, the maximum allowable capacity shortage to 0, it will always meet the peak load.
Peak
But
load.
there'll be times
Hmm.
where, in this case, where, because if the peak load is greater than 20, actually, Homer requires a certain amount of operating reserve as well. That's a more advanced topic, which we'll get into on the fifth day.
Yeah, on the multiple genset topic.
Yeah.
So,
Right.
so is it possible that in case of a peak load exceeding 20 kilowatt, it is recommended that both generators should be running in parallel just to cover up that peak load?
Right. And there's extra equipment required for generators to run in parallel. So that's a whole nother issue, really.
So just for the information of the participant, this is an interactive session and I would like all the participants to pose as many questions as they can just to clarify their queries. And if there is any confusion, you should just ask questions at this time with the experts. Thank you.
Right. So Silver, I'm sorry I've interrupted you a million times, but you should carry on. Pick up wherever you have lost track.
Yeah, we're good. As mentioned, this is an interactive discussion based on questions that the audience may want to clarify. So I'm just changing the names. So Homer tries to look for the most efficient combination based on the given load profile. So and also based on the, as mentioned by Peter, based on the, if we go to constraints, which we will discuss on the fifth day, there'll be allowable capacity shortage. In this case, we're just using 0. That means all the load will be provided. So this is again the combinations of the gensets that will fulfill all the load requirement without any capacity shortage. Want to add something, Peter?
No, but before the evening's over, I think I need to make a point about tomorrow. And I should have done this at the beginning of the day, but I've got an appointment, which means I'll be late tomorrow morning. I won't tomorrow evening, whatever. On the third day, it's evening for me. I won't be there right at the beginning, and I'll come in. I'm not sure exactly when, maybe 15, 20 minutes into it or something. I don't, not sure exactly when I'll get free, but I just thought it's important to let you know that I won't be there right when it starts tomorrow. A bit of a non sequitur, sorry. So carry on.
We'll be discussing on adding PV and battery and converter tomorrow.
Yes.
Just for advanced information. Okay. Any other questions from
Yes,
the
yes,
participants from the audience?
yes, we have two, three questions. One question is from Adhisha Gunatilki. I would request all the participants to just mention their country name before posing the question. So, is there a way to add capacity charges of the generator, the cost of keeping generator ready when load is not dispatched?
I'm sorry, the cost of what? Say the last sentence again.
The cost of keeping generator ready even when load is not dispatched. I, I
Well,
think
It will be conserved.
idling condition of the generator, the cost of putting it idle.
well, our experience is that a lot of times people will run the generator at its minimum load, and then it can pick up load instantaneously. Um, I, I, I'm not familiar with people letting a generator just idle. Um,
Okay. Maybe we
That's
can ask.
capacity reserve.
We'll ask just this person to just clarify this question again. We move on to the next question, which is from Mohammad Ali Qureshi. The question is, what does dispatch mode represents like CCLF, etc.?
Okay, Peter, you can
yeah,
do that.
I'm happy to talk about that. And we're getting a little ahead of ourselves, but I'm totally happy to talk about that. And it's really only relevant when there's a battery. Um, so CC stands for cycle charging, and LF stands for load following. And the difference is very specific. Um, this assumes you have a battery, and if the battery is big enough to meet the load, Homer will use the battery and won't use the generator. But if either the load is too high or the battery state of charge is too low, and the battery can't meet the load, then Homer will turn the generator on. That's true in both cases. The difference is under load following, the generator will come on and it will simply follow the load. It will simply meet the load. And if there's, I'm oversimplifying slightly, but whereas under cycle charging, if the generator needs to come on, you might as well charge, and the battery is the state of charge is too low to meet the load. Well, let's charge the battery as well. So the difference is just under load following, the generator never charges the battery, almost never. There's one exception to that. And under cycle charging, as long as the generator is on, it's going to charge the battery as much as it can. So that's the difference. So it's pretty straightforward, and it's sort of interesting because sometimes load following is the best option, and sometimes cycle charging is the best option. And we have another dispatch strategy called combined that often is the best of both worlds. We can't. It only works if there's a single generator, though. So.
Okay. We have a question from Asad Iftikhar. One thing of crucial importance while sizing gensets is the dispatch strategy / order being utilized. Will the training at any point cover MATLAB link functionality for this? Are the various control methodologies?
Well, yeah, so I'm glad you pulled that up. So there's the first two, cycle charging and load following, are what I just described. The MATLAB link is actually quite an advanced topic. You know, it's you have to know how to program in MATLAB. But you can I'll speak briefly about it. You can do anything you want in MATLAB, and you can create whatever dispatch strategy you want in MATLAB, and Homer will use your dispatch strategy. You know, it sort of calls an external MATLAB program to do that. We can do that in C++ as well, which is a lot faster and better in a lot of ways, but harder to do. Then the other one he was talking about, which I think we're going to get to on the fifth day, is this generator order. So if you have four or five, if you're a big, if you got a regular utility plant, you've got 4 or 5 or 10, whatever generators, and you dispatch them in a certain merit order, I'll just dispatch this one first. If the load's too big, then I put in the next size up, and et cetera. You can that's what the generator order dispatch strategy allows you to specify that. and that's part of the day 5 training. And then I mentioned combined dispatch, which is sort of it intelligently switches between cycle charge and load following. Predictive is new. It's really from Homer Grid, and we've it looks ahead. It's actually pretty complicated, and it is, you know, because it looks ahead and says, oh, we're not going to make it through the night. I better charge the battery now instead of waiting for the battery to get empty, for example. Or, you know, it knows that tomorrow is not going to be a sunny day or whatever. So it's actually really useful in our Homer Grid software. So I'm not going to talk about that anymore because I don't use it in Homer Pro very much, frankly. Inter time step is sort of interesting. We had a project with NREL just last year, and they came up with an algorithm for incorporating the variability within a time step. So if you're doing 1 minute time steps, it's not probably that important on the solar. If you have solar resource data at a 1 minute resolution, it's not that important. But at a 1 hour resolution, you have a data point that says, okay, we've got 5 kilowatt hours per square meter for this hour. Well, it's not necessarily going to be 5 kilowatt hours per square meter for the whole hour. There's going to be variability within the hour. And this is more important for larger systems when you worry about things like inverter clipping. And if on grid connected systems, if you can't there's limits to what you can export. Using an average won't get that clipping correctly. So this is a sort of advanced topics for larger systems, really. And it's at beyond. We could go into more detail in an advanced training on that. The important ones for these smaller systems are load following and cycle charging, and the combined dispatch strategy. And if anybody's doing stuff in MATLAB, we'd love to hear about it, and it'd be very interesting to hear what you're doing. Okay, back to you, Silver, unless there's another question.
We have another question from Mansoor Rana. Can we model the combined cycle generators in Homer? If yes, then can Homer decide on its own that whether to use the open cycle configuration of the combined cycle generator or just the combined cycle configuration in that case?
Homer can model anything that converts fuel to electricity. Homer can model that. So that's what we call it, a generator. It could be a fuel cell, could be a turbine, anything that converts fuel to electricity, and you just define the fuel curve. But he mentioned a combined cycle where you have the option of just using the gas turbine without the steam turbine, without the bottoming cycle steam turbine. So that would be a pretty complex fuel curve, frankly. So nobody's ever asked us to do that because that's more, Homer. That's the smallest combined cycle. I used to work with a company that developed combined cycle plants, and they're large plants. They're not for well, the bottom line is we can model it, but we can't do the specific thing that he was asking, which is separate out the gas turbine and steam turbine and model them separately. That's not something Homer does.
Okay. So over to Silverio, then please continue.
Yeah, we have. I think we have covered the topics for today. Unless we want to have a preview of the following day, what do you suggest, Peter?
Well, I was going to go to lesson B5 and
yeah. Okay.
why not?
All right. Yeah. So we can proceed to parts of the topic tomorrow. We can add. Uh, let's see. We can add battery, PV, and converter to the system. Okay. Okay. Yeah, maybe we can go back to our original configuration. So uh, let's do that. So for the small genset, we'll put in. Sorry, I see the screen. We'll put the 25, and then for the medium, we'll put the, or we'll just add the 50 that we originally installed. Okay, so just to simulate this.
So, a question for Peter and Silverio. This
Yeah.
Homer, it basically evaluates based on the requirements of the load and the power sources, and then recommends you on the basis of low cost. So, does it takes into account the environmental aspect also? It gives you some kind of emissions, which one option would produce, something like that.
Yeah, absolutely. Um, and right, there you go.
Yeah, one of the outputs of Homer on the models that it selects, it also shows the emissions. So CO2, carbon monoxide, unburned hydrocarbons, particulate matters. This all depends on the contents. Let's say if we look into the genset, the fuel.
It's under resources, fuel. Fuel's considered a resource.
So here, it defines the contents of those of what's in the fuel type. So
Yeah,
for the
if
diesel
you
that we're
double
using,
click on it,
okay, here. So for the diesel that we're using, it assumes that you have the calorific value in megajoules per kilogram, then the density, the carbon content, and this type on conventional, and of course the other parameters. So if you have more, let's say, details of or other values for these numbers here, let's say some variations, you can also modify the, the contents of your diesel type. So that also holds true for other types of fuel that you may want to for your engine to use with the variable, with the parameters that you can use based on your requirement. So yeah, Peter.
and you can create your own fuel by changing these numbers, changing the name up here at the here up on yeah. If you change these values, you can copy it to the library, and you have a new fuel that So if you want to, like, I don't think we have heavy fuel oil in here, or
Yeah.
actually, I could show something if you want. I can take over the screen
Okay.
share.
Yes, you can take over, Peter. So if you want to explain about the
Yeah.
fuel type and fuel contents.
Okay, so I've got to rearrange my screens here for a sec. Show my screen. Okay, whoops. Which screen am I showing? Hopefully I'm showing Homer and not you guys'
The folder.
faces.
Yeah, you're showing the folder for lessons ABC.
Oh, I don't want to do that. Hold on. Oh boy, how do I change which screen I'm sharing? Oh, here we go. Here we go. Hold on. Sorry. Stop sharing.
Okay, till the time just Peter carries on with it, we have a question. Can we optimize emissions using Homer software?
Depends what you mean by optimizing, but we can minimize the carbon emissions, for example. I mean, minimizing the carbon emissions is pretty much the same as minimizing the fuel consumption. And so, you can build 100% renewable, and you'll have no emissions. But let me show you what I think is a more fancier way, a better way to do that. So there's three things. Silver showed you here the emissions tab on the results. And he also showed you the fuel inputs. On the generator side, hold on a second. On the generator side, under advanced, there's an emissions tab here because the emissions are a function of both characteristics of the fuel, like the sulfur content primarily, and the carbon content. But some of the carbon ends up in carbon monoxide. That's a function of the generator, and unburned hydrocarbons. So it's the carbon dioxide emissions is all the carbon in the fuel minus the carbon that went into these two things here. And things like particulate matter is a function of the generator, and nitrous oxides, that's a function of the generator. But what you can do under project emissions is, and this is, I think it's better than actually trying to minimize. If you try to just design the system with the least carbon emissions, it's just going to be 100% renewable. That's the answer. So just design me the least cost 100% renewable system. Okay, but what you can do, which I think is really interesting, is you can either put a penalty on it, a carbon tax, dollars per ton, so or carbon pricing. This is where you would put in carbon pricing, and you can do a sensitivity on that, so you can see as you ramped up the carbon pricing, you're going to make fuel more expensive, basically, and the least cost system is going to have more renewables, more batteries, and use less fuel. And at some point, what carbon price will make the 100% renewable, zero emissions system the least cost system? Well, if you do a sensitivity on this value, you can figure that out. So there's two ways to do it. You can either put a penalty on it, dollars per ton, or you can put a constraint on it that says, okay, design me the least cost system that emits no more than, whatever number you put in here for carbon emissions, and do a sensitivity on that. And that, I think that's really interesting, because you get an interesting curve that shows, well, I can reduce my carbon emissions with very little cost up to a point, but once I'm at like 90% renewable or something, but getting the last little bit of fuel out of the system is more expensive, and it's sensitive to your reliability. All these factors interact with each other, which makes it, well, one, it's why an optimization model is so valuable, and two, it's why this is such an interesting problem, actually, because these things all interact with each other. So it has quite a lot of emission modeling capability. We've sort of deviated from the training manual, but that's good. I like responding to questions. Are there any other questions?
Yes, we have a question from Nadhira Primadasa. The question is, can we use a customized operating strategy in Homer?
I think that's the dispatch strategy.
Yeah, that's what the MATLAB link is for. There's two ways to do it. MATLAB is the easiest, but you can also do it. We have a software development kit that you could create your custom dispatch strategy in C++, and then that runs really fast. And if you want, we can put it into Homer. We did that with ABB. Actually, ABB created their own custom dispatch strategy. We put it into Homer, but then they changed it, so we didn't keep it in there. But yeah, if you want to create your own dispatch strategy, that's what the MATLAB link is all about, right? Okay, well, I'm going to move on, and just to show a couple of things, like here under PV, we've been using the optimizer, which just lets Homer just search around and find the least cost system. But we can also put in a search space here, and say, no, I want to look at very specific sizes of PV. And so, like in this case, Homer said the least cost system had 39 kilowatts of PV. Well, you probably can't get 39 kilowatts.
Yeah, your roof is not that wide, or you don't have space. Yeah.
Well, maybe you don't have space, or maybe it has to be laid out in strings, and so
that's right.
So maybe you can do 36, and you can do 40. You can probably do 44, probably do 32. And so instead of Homer just checking everything, including 39.4 and 39.8, it's just going to look at those sizes that you gave it there. And you could do the same thing with the battery. Right. So why don't I do the same thing with the battery? So in the least cost system had, what is it? Had 76 kilowatt hours of batteries. So that's a lot. That's a fairly big battery bank. We're using a
Lead acid 24 volts bus.
right. Well, it's this battery here is a 12-volt battery.
Yes.
Actually, you're actually pretty constrained on batteries. They have to be in strings. And you can get a 2-volt battery, you can get a 6-volt battery, you can get a 12-volt battery. But for large battery banks, you probably want, in this case, we're going to have a 24-volt bus, which means there's going to be two batteries per string in series. If you put batteries in series, the voltage is doubles. If you put them in parallel, then the voltage stays the same, but you get twice as much current. So anyway, so now this is just a number of strings. So and when we have 76 kilowatt hours, so we want actually I'm gonna do something different. I'm gonna make it a 48-volt bus. So they come in fours, and so 76 would be 36, 18. We'll look at. Well, the truth is, you really don't want too many parallel strings. So we probably want a different battery. We probably want a much bigger battery than the 1 kilowatt hour battery is really handy because the number of batteries, the number of kilowatt hours, it makes it really easy to understand. Whereas if you go into our catalog here, we've got a huge selection of batteries, but their capacities are not nice, clean integers. But if I wanted 76 kilowatt hours of storage, I'd want to use a bigger battery. I'd want to use either a bigger battery or a smaller voltage so that you could put more batteries in series. So, I'm doing this on the fly, which is not always such a great idea. But if I took this battery here, which is a 48-volt battery, let's try that. So we're gonna do that instead of this generic battery. It's already a 48-volt battery. So we're gonna look at 1, 2, 3. How many? 15 kilowatt hours. 3, 4, 5, 15, and 6. So now it's just looking at the options I gave it to look at. Huh, that's interesting. Didn't find a feasible solution. Huh, I'll be darned. This is what I get for trying to wing it, you know. So we'll just make everything bigger. I don't know why that didn't work, to be honest. 48, 54, let's say. Just out of curiosity, we've got this genset here. I mean, hold on a second. The peak load is what? Yeah, I should never try to do things on the fly during a training. Oh, I know. Haha. It's because I left these emission constraints in. I was like, what? Oh, geez. Stick to the manual. Oh, well.
Yeah, it will not allow the genset to operate then.
Yeah. Right. That was
There you can see
so
the solutions.
yeah. And it's actually, you know, an internal rate of return of 17% or a payback of 5.5 years is pretty good. And
Yeah.
you know, here we're comparing the diesel only system, which doesn't cost much initially, but it costs $32,000 a year to run. And this
Because of
system only,
fuel.
mostly because of fuel, right? And this system only costs $8,500 per year. And the cost of energy, we've now gotten down to 30 cents, which is really good. And we've got these warnings here. The PV search space may be insufficient. That's interesting. So I'm going to look at that. So it put in as much PV as I allowed it to. So I'm going to go back and because of that warning, I'm going to go back and put in more PV and more batteries. I should also check the converter because maybe the converter is not big enough. Actually, I'll tell you what we'll do. We're going to use the optimizer for the and put in, you know, so now it's going to search on its own using its own algorithm somewhere between 0 and 50 for the converter. But and a handy way, instead of, if we have these little buttons here, search space, you can get to it here, or you can get to it here, and you can look at all of the decision variables at once. And the lower graph is showing you which ones were sort of at the limit. So we
you
know
can
the
see that the genset is on the limit and also the PV is on the limit. So Homer would recommend extra larger system, so you're not on the edge.
Well, both also, the PV and the battery are at the limit. So we're just going to make them both bigger. We'll make them a lot bigger, just so.
Peter, can I just throw a quick question?
Sure.
This is from Shoaib Ahmed Khatri, does Homer support multi-objective function optimization? That is minimizing capital cost and NPC.
Well, it gives you all the data you need to do that. You know, we've talked about. Well, I'll show something in a minute that makes it easy to do that. I mean, net present cost is effectively trading off capital and operating cost. So it's doing that automatically. But if let me show you something in just a minute. But see here, you can see we got it did want more PV and batteries, and we've got brought the cost down even further. And it's 87% renewable. I mean, the gen set is running for less than 1,000 hours a year, and compared to the all diesel case, it's literally 90% reduction in fuel consumption. So that's really excellent. So there is a graph that I think is really interesting, a lot, where it's showing here's all the systems that it's simulated, and the defaults are operating cost versus capital cost. So you can see the trade-off there, and this frontier, the systems along this line, the boundary here, are the potentially optimum ones, basically depending on your discount rate, how you would trade off capital versus operating cost. But you can change these axes any way you want. So you could trade off and you can see by hovering over each of these, like that's a smaller PV array, but still the big battery bank. And then over here, this is a larger PV array. I think that's the one that Homer thought was the least cost system. But depending on how you trade off capital and operating costs, any of these systems along this envelope here, or whatever, the southwest frontier here, could be the least cost system. It's the function of how you trade off capital and operating costs, which is the function of the discount rate. These systems up here are never optimal, but Homer had to search around to just, figure that out. So this is actually kind of a advanced topic in a way, and you can see you have a lot of flexibility about limiting what you're displaying. Let's see. So I know. There's one other thing that's worth talking about, I think, and that'll probably be it for the night. Because this is something that some people sometimes find confusing, is that here's the search space, and over here you also have, it says capacity. This is the cost table. So this portion of the interface here is defining a cost function. And if we hit the more button here, we can say, okay, well, if it's just a small PV array, it's $2,500 a kilowatt. But if I have 5 kilowatts, it's not going to be it's not going to be $2,500 each. That's what it just calculated. We get economies of scale, and so maybe it's only 10,000, and we'll make this 9,000. And then if we go even higher, let's say we go to 20 kilowatts, it extrapolated, it calculated the slope between these two and extrapolated, but we said, no. We get an even bigger discount if we go that high. And then, and also, yeah, big discount on the, wait a minute, I did something wrong here. Hold on a second. I left out a 0. There we go. And so these dots here are these sizes over here, and it just shows you the formula that's using. So frankly, I should have gone higher. So 50. Just to show this is the economy of the scale, how the cost, you can define these costs. I'm winging it again, which is dangerous. So you can define, there's different ways to talk about this: volume, discount, or economies of scale. Just things get cheaper if you buy more of them. And so you can define that here. And that's really important if you don't know what size you want. So that's a useful feature. The other thing on this cost table, so just to be clear, this function is this table, excuse me, is defining a cost function. It's just coming up with a mathematical formula that if it's the size is this, here's what it's going to cost. And these numbers over here are what Homer's actually going to model. And they don't have to match because Homer interpolates. You know, you can see if I delete, well, never mind. If I delete some of these, the dots will go away, right? The other thing that's worth talking about is we can do a sensitivity anywhere there are these round buttons, right? But doing a sensitivity on the cost when you have multiple costs like this is a little tricky. So instead, for the cost sensitivities, it's a multiplier. Instead of, for the other values, we put in actual values here. Here we're just putting in a multiplier. So we would say, well, okay, that's the cost. That's what I think the cost is, but I might be high. I might be 10% high. I might be 20% high. So now it's going to multiply all these numbers by 0.9 or 0.8 when it does the sensitivity analysis. So it's a little more complicated, but it's the only way to handle when we have multiple rows here. So I always think that it's useful for people to understand that. Right. So I hope that was clear. I'm just going to look at what the next thing we were going to talk about was. We optimized the size of the, oops, okay. Oh, so I left in this complicated cost function, and we optimized the size of the converter. That was the next lesson.
Peter, we have a question.
Sure.
We have a question from Dr. Nawaz Ahmad. He is the director of our center. Can we see levelized cost per unit of energy generated over project life?
Well, absolutely. That's this number here, cost of energy.
Yes.
Right.
So we have these different costs of energies for different options.
Right. Right. Absolutely. But it's a levelized cost, so that's well, just like he asked, the cost of energy levelized over the whole life of the project in real terms. You know, so Homer does all of its analysis using real costs as opposed to nominal costs. So if we go back here on the home page, it's asking for the this is the nominal discount rate, and here's the inflation rate. Actually, it's probably easier to see on the economics page. So we have an 8% nominal discount rate and a 2% expected inflation rate over the life of the project. And that gives you a real discount rate of 5.88%. And this is what Homer actually uses. And when we were doing, let me show the multi-year, because now that we have PV, We can put in PV degradation over the life of the project. We have fuel now, so we can have fuel price escalate. Here's the load. We already talked about that. And we had this before, and I didn't talk about it, but I'll talk about it now. On the economics screen here, we have the discount rate and the inflation rate and the project lifetime, and we have the capacity. Before we put in over here on the home page, we have a maximum annual capacity shortage. It's also you can see it here as well, and that just says you have, like, if this is 99, if we put in maximum annual capacity shortage of 2%, what we're saying is we have to meet 98% of this load. It's a constraint. And if it doesn't meet 98% of the load, the system's not feasible. That's what the meaning of this is. But over here on economics, instead, we can say, no, you can, well, if you're allowing capacity shortage, you can allow the capacity shortage, but penalize it. And so that's the way a lot of people think about this, is that well, there is going to be some capacity shortage, but we don't want to make it free. We want to penalize the system or that capacity shortage. Anyway, that's the meaning of this one. But what I wanted to talk about were these two here: system fixed capital cost and system fixed O&M cost. So these costs don't affect the optimization. They don't affect the decision between how many batteries, how much PV, how much fuel to use, etc. They simply add costs to the system. So it shows up in the cost of energy, and it shows up in the and it does it in two different ways. The capital cost is where you would put things like your development costs, or if you have to build a road, and you're going to have to build a road regardless of what kind of system you install, or the house, or the generate. You have to build a little structure for the generator and the batteries, and you're going to have to do that regardless of how big the batteries are, or how big the generator is. And so that's a capital cost. That's a one-time upfront cost, and so that's what this number would be. And that's if regardless of the system design, it's a cost. And so development costs would typically go there, and a whole variety of different kinds of development costs. But then there are other costs, like administrative costs, that are ongoing, that are every year. You've got your operator, and you're gonna, regardless of what the system is, you're gonna have an operator, or you're going to be running a little utility company, and you're going to send out bills, and you've got an administrative cost about running the system, regardless of whether it's diesel or PV, or how big the PV array is or anything. But it's going to be every year. So you can see this system fixed cost is just dollars. It's a one-time cost, and the system fixed O&M cost is dollars per year. So these will enter into your cost of energy. That was actually a good question. I mean, the simple answer was, yeah, their cost of energy is right there. And I didn't have any system fixed costs. But if you did have them, it would increase this cost of energy here.
Thank you, Peter. Peter, another question, while you were referring to this PV degradation values, obviously these PV's power will reduce with time up to like 70 to 80% of power by year 20, or after working for 15-20 years. So does HOMER incorporate this thing? So if not, then why do we put these values inside the software?
I'm sorry, I didn't actually hear all of that. Could you repeat that?
Yes, what I meant was that if you are installing a system of 10 kilowatt solar PV in a community, and you know that with period of time its power will degrade, and then it will not be able to give the same amount of power after 15-20 years. So what I mean is that this value of this degradation value, if you put it into the software, does it recommends this system to you after incorporating that degradation value or not?
It will only incorporate the degradation value if you put it in here. Like so you know, and you have to be using the multi-year because it's a multi-year phenomenon that the PV degrades. So you know, PV degrades, you know, something like 0.5% a year. So after 15 years, you've lost something like 7% of your capacity. So it'll incorporate that, and if, out in year 25 or whatever, if it'll upsize the size of the PV to make sure you can still meet your load in year 25. And this is actually more important for the battery. Well, we have three different. No, this is a complicated discussion. We have three different battery models. A really simple one, the one we used for a long time called the kinetic battery model, and we have a new, relatively new, advanced model that really does a good job of calculating battery degradation if you have the input data for it. And our new software for Homer Front for large projects, which we're really not going to talk about, but you know, we're at the end of the evening. Well, my evening. We're at the end of the training period. Our new software will do this thing where it'll augment the battery bank. Like if a battery loses 10% of its capacity, it'll put in 10% more batteries, and it's because the large developers really focus on that. Now that people are putting in really large battery banks now, so it's a whole different project kind of.
So, Peter, we have just 5 minutes left. We have quick 3-4 questions.
Oh wow!
So I would
Okay.
like to be very brief in your replies to them. One question is from Shakir Shakur. Is it possible to incorporate mathematical cost function in Homer instead of entering values in table?
You can't enter a function. You can't enter an equation into Homer. I think that's what he's asking. But
Yes.
we've built Homer in a way so that it will create this function based on your inputs, but it doesn't have like a function reader. No.
Thank you. We have another question from Asad Iftikhar. Is there a report generating feature in the software? Any plans on incorporating this in the future?
Oh, that's a really good question. So see here it says create proposal. So you've done your analysis, and you've decided this is the system you want to run with, and so we have a proposal writer, and it actually is two different formats: a really detailed one, which is for engineers probably, and one that's probably more appropriate for showing to a client. And so we have this little wizard to help you create it. So you can put in, you know, who's it for, you know, what their title is, et cetera, the project address, and then you know my name and my title and contact information, and then company information. I could, you know, this is my company, although we've got to change the name now. But and then any text I want there, and even important the logo and even import an image. And if you want to put in some a testimonial or something, you can do that. You can add another one, you know, whatever. Wait a minute, what's going on here? Oh, I have to put something in here. Okay. And you can customize it so that you know, if you don't want all this detail, you can take it out. And that time series viewer that Silver was showing, you can create graphs in the time series viewer and then include them in the proposal, which I'm not going to do right at the moment, but you can do that. And then they're, you know, different paper sizes. And I'll show you what it looks like. I did this really quickly. but and it's down on my other screen here. So then you have a proposal that looks like this, and this is all customizable, but I didn't do that just now. And then page down, so here's this is customizable, but then it's got, and then here's my little thing I wrote. And then here's a lot of useful information. Oh, I need to keep that answer short. So there's a lot of stuff here, including some explanatory material, etc. So what was the next question?
Okay. So next question is from Dr. Nawaz Ahmed again. Is it okay to say that actual system selection and project decision making depends on the levelized cost of energy generation, for example, in USD per kilowatt hour?
Let's see if I understand the question. Actually, I'm not sure I understand the question.
Well, what he meant is that the system proposed or system recommended by the HOMER software, does the decision making depends on the levelized cost of energy generation?
Well, net present cost and levelized cost of energy move together. So the system that minimizes the net present cost also minimizes the cost of energy. So they're optimizing on one is equivalent to optimizing on the other. There is a minor exception to that, which I could go into tomorrow maybe. But I think that's what he was asking, right?
Yes. Yes.
And
So
there was
we have a, yes, please go ahead.
no one more. You go. One more question.
We have a question from Ahmed Tala. When does the multi-year inputs mode work? In the current example, if I click enable in multi-year inputs, it shows multi-year optimizer not supported.
Oh, that's a good point. That's a good point. So multi-year doesn't support the optimizer. So this search space, it'll work with the search space. Over here on the battery, we have a search space, but over here on the converter, we're using the optimizer. So if we wanted multi-year, we'd have to go back to the search space. And that's just a mathematical programming limitation that we have. And it's also for your convenience too, because the optimizer takes longer to run, and multi-year is going to take longer to run. 25 years is going to take 25 times as long. So, it's if you can get carried away with doing too many sensitivity analyses in one run, and then you do multi-year, and maybe you've had 1 minute data, and HOMER will take days and days to run if you do all that. So multi-years is 25 years is 25 times slower. So you have to think. You don't want to get carried away trying to do too much in one run.
Okay, thank you, Peter. I think we are over with today's session. It's already 12 o'clock. Peter has to go to sleep now, I suppose.
Yeah, right. And just to remind you that Silver is gonna start tomorrow, and I'll join whenever I get home from my appointment. But
okay.
it shouldn't be too late.
No problem. Okay, so in tomorrow's session, ladies and gentlemen, we would cover the interconnected mini grid designs, net metered PV systems, feed-in tariffs, PV and storage for interconnected microgrids. So with this, I may like to conclude today's session. Thank you everyone for attending the training. We had to listen to some excellent presentations delivered by our distinguished presenters. All the presentations and the content of this training are available on SAG Energy Center's website. We will meet tomorrow again at 10:00 hours Pakistan Standard Time. You can use the same web link to get connected for tomorrow's session. With me signing out, thank you again for joining us today and looking forward to see you tomorrow. Have a nice day.
Yep.
Bye-bye.
Thanks, everybody. Bye. See you tomorrow. Bye now.
Thank you, everyone. Bye.